This is a quick video on lattices and other places truth values live. Okay, so there's kind of 3 points of view. There's 3 points of view. Okay, there's kind of an algebraic point of view. There's kind of a Poset point of view. So partially ordered sets. And then there's this kind of a categorical point of view. The translation between them is not difficult. Okay, so let me just start by drawing the big diagram. Okay, so here is Posets. So let's. Okay, so these are Posets. Among Posets, we have so semi-lattices. Okay, so semi-lattices should be quite big. So these are semi-lattices. Okay, so what are semi-lattices? So these are going to be single operations. Okay, so I guess I'll write the axioms in here. So they have so they're commutative. There's sets with a binary operation. And then they have this, they're associative. So B. So I'm just writing it here with this OR symbol, or the join symbol. It doesn't matter what symbol I use here, it'll be the same. So we'll have this. Okay, so this is this thing here is the idempotence. Okay, and okay, so this is what lattices are. These are semi-lattices when you have one operation. Okay, so inside this, we're going to have lattices. Okay, and lattices have the additional operation. So they're going to be two guys here, and these are going to give you these semi-lattices, and then they're going to interact. And the interaction is via these absorption laws. And the other absorption law is A OR, and B is A. Okay, so now is where things will kind of mix up a little bit. So here we are going to have two things here. So let's talk about. Let me make two circles. Try and make them rather big. Okay, so here, and then here. So these are going to be bounded lattices. And then here are going to be distributive lattices. Okay, so these things have two constants, 0 and 1. So they have like a top and bottom element. So A, and then this is A and 1. This is A. Okay, and then, okay, so then I'll say a little bit more about what's inside here in a second, but let's talk about distributive lattices. So these will have the distributive property. Okay, and you only need to get one of the distributive axioms to prove the other. So B or A and C. So let me just say this, the other is for free. Okay, and then inside here is where things start to get interesting. So let me just say, I'll try and draw it, then I'll write the axioms on the next page. Okay, so these are Heyting algebras. And these are Boolean algebras. Okay. Okay, so let me just say maybe I can. Okay, so let me just write maybe like I don't know how I should do this. I ran out of space. Damn it. Okay, let's do this. So this one has the implication arrow, and this has a not symbol. Okay, let me go and do this on the next page. So now we want to zoom in, and we're going to look at Heyting algebras and Boolean algebras. So Heyting Boolean. So and then here is Boolean algebras. Okay, so this is going to be, we have this symbol here, so we're given this extra symbol, and it satisfies, okay, so that this thing is the top element, so it also has that A and A implies B is A and B, and B and A implies B, B, and we have also a distributive law. B and C. So this is, okay, maybe I should write it like this. Okay, so this is the binary operation here. So A implies B, and A implies C. So in order for something to imply it, it needs to imply both of them. Okay, so these are the axioms that you have. Oh, okay. And then from this, we get this auxiliary definition of the pseudo-inverse, where we define not A. So this is equal to A implies 0. Okay, so the freebie we get, so a freebie okay, the freebie that we get is that A and not A is false, and we don't get, so the kind of weird thing here is that so and A or not A is not equal to 1 in general. Okay, but inside the Boolean algebra, so okay, in here, sorry, I shouldn't have written words. Let me get rid of that. For Boolean algebras, we have we just get this operation. This thing. Oh, dang it. This not operation. So sometimes people write it like you know, like that, like not. Anyway, so we have this not operation, and this one satisfies the usual axioms, the classical axioms. Okay. All right. So that's all we want to say. So okay, that's what we want to say about Heyting in Boolean algebras. So I just want to say a little bit about the conversion between Posets. So the conversion the Poset an algebraic point of view. So the algebraic point of view is again a set with a binary operation or a couple binary operations and constants and so forth. It's an algebraic theory. Okay, so B okay, so this is or. So this I'm going to tell you how to convert between the relation. So I'm going to tell you how to convert between the partial ordering and the binary operation. Or A is equal to A union B. Okay, so this is the same thing here as B is less than or equal to A. Okay, what else do we have? So we have so this thing here will correspond to the least upper bound over in the ordering side, and ands will go to greatest lower bounds. The other things that we have is that so true. So we use this symbol sometimes for true. This corresponds to the maximal element. And this thing here, so this is false. This will correspond to the minimal element. Okay, so this is the basic way to convert between the two things. So I just want to say a little bit more about the categorical perspective of propositional logic. And to do this, I'm going to just give some definitions. So we're going to be converting posets into categories is the idea here. So a preorder category or just a preorder is a category where all objects were have at most one morphism between them. Okay, so then let me give another definition. A skeletal category, a skeletal subcategory, of a category C is a subcategory, let's say S contained in C, where the inclusion is an equivalence of categories, and it's the smallest equivalence. So it's a smallest subcategory where this inclusion is an equivalence of categories. Okay, so so then I can say a definition: a category is skeletal. If it is its own skeleton. Okay, so that's just a terminology. So so the idea that I want to convey now is that posets are skeletal preorders. Okay, and okay, so here we have a relation, a binary relation, and this will convert to just a morphism over in a skeletal preorder. Okay, so that being said, we can formulate many lattice theoretic notions categorically on using skeletal preorders. Okay, so for example, we can look at meets. Okay, so if we look at the meet operation, so this will correspond to products. So the category having products. So if your poset has meets, then this will have products. So note that meets have the property that R is less than or equal to P and Q implies that R is less than P and R is less than Q. Okay, so in terms of, so Okay, so let's look at what this means here. So this thing means that if we have a map R to P and Q, and we know from the axioms of the meet here that we have maps like so, P and Q. Okay, but so from this we're going to get maps here and here. So R is going to be less than P and R is going to be less than Q. Okay, so joins are going to be coproducts. So what's the axioms here? So P or Q less than R. So this is going to imply and Q less than or equal to R. So now we can write this out diagram theoretically. And so here we have P or Q. Okay, and we're given these guys here. And so we're going to have, so we have a map here to R. Okay, and this will give us these maps. Okay, so this is kind of the universal property for coproducts is encoded in this. Okay, so we can continue this. And this is, it gets a little more interesting here. So we have P and Q. So this is for implication. So now if we move past this, so we have implication. So this is true when we have this. Okay, and this implication will correspond to a certain adjunction in the category. And in particular, what we can do is, so let me just say what it is that for Q, we're going to have an adjoint pair here of functors. Okay, so in particular, amorphism, we're going to have a morphism here to R. So then this thing is the functor, right? And so I'm going to move it over. So the adjunction is going to be over here. So then if and only if we have the following map from P to Q implies R. Okay, so this is the idea here. So we're going to have these functors. So we have these two functors on the category. So this is interesting that you even have implies in terms of implications. Okay, then the other ones are kind of stupid. So so we have a bounded lattice here. So this is going to be the same thing as an initial object. Okay, and then this is going to be a final object in terms of the category. Okay, so the idea is that so the punchline is that a Heyting algebra okay, so this is a skeletal preorder with products, coproducts, terminal objects, initial objects, and adjoints. This guy here. Okay. I want to make some other observations. So the rules for deduction come from replacing this symbol with the implies or the proves symbol. Okay, and so so kind of the reflexivity and transitivity of this symbol are already captured from the axioms of categories. Right, so that you can compose morphisms and there's identity things. Okay, and so, and I guess I should also say that this, what we've done here is, I've only made it up to now, and I'm going to just kind of repeat this, I've said this before, or I don't know if I've said this before. So this is intuitionist, blah. So this is intuitionistic logic right now, where we only have the implication. To get this to be classical, okay, for classical logic, well, we need to suppose that not P gives a map to P, okay? So, and we get to define not P for free. So we don't need, we kind of get it for free, where, so not P is defined to be that P implies 0. Okay, so the other one. So, okay, and also for free, we can derive the following proposition, so that if we have this thing, this implies okay, so this would make it false. Okay, so all right. So this is what we get to prove. We get this for free, but then we don't get this. So this is something that we need to impose. So this needs to be imposed. For classical logic.